Midday in the Jordanian desert, the sun hits the red sandstone at 110 degrees Fahrenheit. In this heat, a human body loses a liter of water every hour. Without shelter, death arrives in a day. Yet, 2,000 years ago, 30,000 people lived here. They didn't just survive, they built swimming pools. They maintained lush gardens in a place where rain falls only a few times a year. We look at the famous treasury facade and see a temple. But we are looking at the wrong thing. The real miracle of Petra is buried beneath your feet. It was a machine made of terracotta and stone, a massive, invisible engine that pumped life into a dead zone. But this machine had a flaw. It required total, unbroken control over nature. And when the earth finally moved, the machine didn't just break. It suffocated an empire. The Nabataeans arrived in this valley sometime around the 4th century BC. They were traders, nomads, who controlled the incense routes between Arabia and the Mediterranean. But they saw something here that others missed. The Wadi Musad, the Valley of Moses, receives approximately 6 inches of rain per year. Almost all of it falls in violent winter storms. Flash floods tear through the narrow canyon, drowning the valley in minutes before vanishing into the sand. For most civilizations, this would be a curse. For the Nabataeans, it was opportunity. They built a grid, not of roads, but of water. 210 cisterns, carved directly into the sandstone hills. Each one positioned at a specific elevation, forming a cascade system that captured every drop of rainfall. The main channels run for over 12 miles, feeding into reservoirs that could hold up to 40 million liters of water. But here's what separates engineering from genius. They didn't just store water. They controlled its pressure. Terracotta pipes, each section carefully fitted, ran throughout the city. The angle of descent was calculated to maintain consistent flow without erosion. Too steep, and the pipes would burst. Too shallow, and sediment would clog the system. They achieved a gradient of approximately 1 in 200, a drop of 5 meters per kilometer, allowing gravity to move water without pumps, without machinery, without anything that could break. They turned chaos into clockwork. Winter storms that would destroy mud-brick cities became their annual resupply. The Nabataeans didn't fight the desert. They reprogrammed it. By the 1st century AD, Petra was the richest city between Damascus and the Red Sea. Not because of gold, because of water. Survival wasn't enough. They wanted luxury. The garden and pool complex sits on the northern terrace, a quarter-mile from the treasury. Archaeological surveys reveal a swimming pool measuring 43 meters long, larger than an Olympic pool, fed by aqueducts that carried water uphill through a series of pressure towers. This required precise engineering, closed pipe systems that could maintain water pressure against gravity itself. In a desert where neighboring tribes rationed water by the cup, the Nabataeans built fountains. But every fountain was a liability. Every pool was a debt against the system's capacity. The more complex the grid became, the more vulnerable it grew. Consider the mathematics of failure. With 30,000 residents, the city required approximately 1.5 million liters of water per day for drinking alone. Add agriculture, industry, livestock, and the luxury complexes, and the demand likely exceeded 3 million liters daily. The margin for error was measured in hours. A single blocked channel could trigger a cascade failure. If one reservoir ran dry, the pressure gradients downstream would shift. Pipes designed for consistent flow would experience surges or stagnation. Air pockets would form. Terracotta would crack. The city employed an unknown number of hydraulic engineer specialists who walked the channels daily, clearing debris, repairing cracks, adjusting flows. Their job wasn't just maintenance. It was triage. They were keeping a patient alive through constant, exhausting intervention. The Nabataeans had built a masterpiece. But masterpieces don't scale. They had engineered themselves into a corner where perfection was the only option. Any degradation, any loss of knowledge, any shortage of skilled workers, any disruption to the centralized authority that coordinated repairs would be fatal. They had defeated the desert by building a machine more complex than any empire before them. And machines break. May 19, 363 AD. An earthquake measuring an estimated 7.0 on the Richter scale struck the Dead Sea Rift. The epicenter was approximately 60 kilometers from Petra. The treasury survived. Most of the rock-cut facades survived. But the machine died. Underground, the terracotta network shattered. Pressure towers collapsed. Reservoirs cracked and drained into the bedrock. The earthquake didn't need to destroy the city's buildings. It only needed to sever the hydraulic heart. What happened next is written in silence. Without centralized water distribution, the population couldn't sustain itself. There's no evidence of mass graves, no signs of siege or slaughter. The people simply left. Petra transitions in the archaeological record from a thriving metropolis to a skeleton within 2 generations. Some stayed. The Bedouin tribes who live in the area today are descendants of those who remained. But they survived differently. Smaller populations, nomadic patterns, reliance on natural springs rather than engineered systems. They returned to simplicity because complexity had failed. The ruins we photograph today are monuments to a paradox. The Nabataeans were too successful. They built a civilization so advanced that it required perfection to function. And perfection, in nature, is always temporary. Walk through Petra now, and you'll see tourists photographing the treasury. But look down. Beneath the sand and the silence, the pipes are still there. 2,000 years later, some of them still hold water stagnant, forgotten, waiting for an empire that will never return. The question isn't why Petra fell. The question is, how long can any system survive when survival depends on never making a single mistake? We still don't know exactly how every component of the hydraulic grid functioned. Some reservoirs have never been fully mapped. Some channels disappear into collapsed tunnels. The complete blueprint died with the engineers who maintained it. Perhaps that's the real monument. Not the treasury's facade, but the knowledge that vanished when the last hydraulic master left the city. In our own age of complex systems, electrical grids, internet networks, global supply chains, Petra whispers a warning. The more sophisticated the machine, the more catastrophic its failure. Stand in the sick canyon at dawn. The light hits the treasury facade, and you see what everyone sees. A masterpiece carved into a cliff. A tomb for a king. A movie set. But this is a distraction. A trick of the eye that has fooled visitors for 2,000 years. While you look up at the stone columns, you are standing on top of the real miracle. Beneath the dust lies a machine. A massive, hidden engine of ceramic pipes, pressurized tanks, and filtration systems that turned a barren desert into an artificial oasis. This city wasn't just carved, it was plumbed. And the story of Petra isn't about the tombs of the dead. It's about the invisible machine that kept the living alive. Until the day it stopped. Everyone photographs the treasury. But the treasury is a lie. Not in the literal sense it exists. It's magnificent. It's 2,000 years old. But it's a lie of omission. A beautiful shell designed to make you forget the question every city in the desert must answer. Where is the water? The Nabataeans knew this. They built their monuments as theatre, grand facades that announced wealth and permanence. But the real engineering, the machinery that made that permanence possible, they buried. Hidden in plain sight beneath the valley floor, carved into cliff walls, disguised as decorative channels. Start with the inventory. 200 cisterns scattered across an 8-square-mile area. Not holes in the ground, but precision-engineered, holding tanks with specific volume capacities, positioned at calculated elevations. Each one a node in a grid. The main aqueduct runs 12 miles from the spring at Ain Musa, but it doesn't run straight. It curves, descends, levels out following contour lines with obsessive accuracy. The gradient averages 0.5 degrees. Too steep, and water velocity would erode the channels. Too shallow, and sediment would accumulate and choke the flow. This is gradient engineering, the same mathematics modern civil engineers use to design urban water mains, executed with nothing but clay pipes, gravity, and 2,000 years of trial and refinement. But here's what makes it weaponized knowledge. They controlled pressure. In the hillsides above the city center, archaeological surveys have identified at least 40 closed-pipe systems. These aren't open channels. They're pressurized conduits using a principle called hydrostatic pressure. The weight of water in an elevated reservoir creates force that pushes liquid uphill through sealed pipes. The Nabataeans built pressure towers, stone cisterns positioned at high elevations that fed lower distribution points through terracotta piping. The weight of the water column created enough force to supply upper-story fountains and rooftop gardens without any mechanical pumps. This wasn't primitive. This was invisible infrastructure operating on principles that wouldn't be formalized in Western engineering until the Renaissance. They didn't just survive the desert, they hacked it. And they did it so quietly that for 2 millennia, no one noticed. Let's reverse engineer the machine. Problem 1. Filtration. Desert flash floods carry tons of sediments and debris, dissolved minerals. Left unchecked, this sludge would clog pipes within weeks. The Nabataeans solved this with a 2-stage system. First, the settling tanks. Large, shallow basins positioned at the entry points of major aqueducts. Water velocity drops, gravity pulls heavy particles to the bottom, and clarified water exits through elevated overflow channels. Routine maintenance crews would shovel out accumulated silt and glamorous work that kept the system alive. Second, ceramic filtration. Some pipe sections show evidence of porous clay inserts fired at lower temperatures to maintain microporosity. Water passing through these barriers would leave behind finer suspended particles. It's mechanical filtration at the molecular level, executed in fired clay. Problem 2. Storage capacity. Petra receives approximately 150 millimeters of rain annually, almost all of it concentrated in winter months. To support a population estimated between 20,000 and 30,000 people year-round. The system needed to capture every drop and store it through 9 months of drought. The reservoir network could hold approximately 40 to 50 million liters enough for 90 to 120 days of total consumption at peak population levels. This assumes aggressive rationing, but the archaeological evidence suggests the opposite. The garden and pool complex. An artificial oasis in the northern sector featuring ornamental pools, channeled streams, and irrigated vegetation. The largest pool measures 43 by 23 meters, with an estimated depth of 2 meters over 1.9 million liters of water used for decoration. This wasn't necessity. This was theater, a demonstration of hydraulic excess designed to communicate absolute control. In a desert economy, visible water waste is the ultimate power move. Problem 3. Distribution. With 30,000 people spread across a multi-tiered valley, the city needed localized access points. Excavations have revealed neighborhood cisterns, small, covered tanks, positioned every 200 meters along major residential zones. These weren't just convenience, they were redundancy. If the main aqueduct failed, localized reservoirs provided emergency supply. If one sector experienced contamination, isolation valves, simple stone plugs inserted into junction points could cut off that branch without shutting down the entire grid. The system wasn't a single machine. It was a network of interconnected subsystems, each with failsafes and manual overrides. The Nabataeans built redundancy into stone. But redundancy has limits. And complexity creates fragility in ways the engineers couldn't predict. May 19, 363 AD, the Galilee earthquake. Magnitude estimated at 7.0, epicenter near the Dead Sea Rift, approximately 60 kilometers northwest of Petra. The treasury facade cracked but stood. The rock-cut tombs survived. The visible city endured. But underground, the invisible engine shattered. Terracotta pipes rigid, brittle, held together by fitted joints, and clay mortar snapped. Pressure towers collapsed inward. Reservoir walls fractured, and millions of liters drained into fractured bedrock. The settling tanks filled with rubble. The filtration inserts pulverized into dust. The earthquake didn't destroy Petra. It severed the hydraulic heart. Here's what the archaeological record shows. Rapid depopulation over the next 50 years. Not a sudden exodus, but a gradual collapse as the machine failed and couldn't be repaired. Why not rebuild? Because the system was too complex. The pressure gradients, the elevation calculations, the filtration staging, this wasn't common knowledge. This was specialized expertise held by a class of hydraulic engineers who likely trained through apprenticeship over decades. When the earthquake broke the machine, it also broke the institutional knowledge required to fix it. The blueprint existed only in the minds of people who were aging, dying, or leaving as the water stopped flowing. By 500 AD, Petra was functionally abandoned. The Bedouin tribes who remained survived differently, smaller populations, relying on natural springs and nomadic patterns. They knew where the old pipes were, but they didn't need them. They had returned to simplicity. Walk through Petra today. Stand in front of the treasury and look down. Beneath the sand, the pipes are still there. Some are exposed now. Archaeologists have excavated sections, mapped junctions, traced the old gradients. You can see the ceramic channels, the settling tanks, the pressure towers, but they're dead. Hollow veins in a body that stopped breathing 1,600 years ago. The tragedy isn't that the machine broke. The tragedy is that the machine was invisible. It did its job so well, so quietly, that when it failed, the world forgot it had ever existed. We remember the treasury because it's beautiful. We photograph the tombs because they're dramatic. But the real miracle, the thing that allowed 30,000 people to live in a place where humans shouldn't survive, was hidden beneath our feet the entire time. The Nabataeans built 2 cities. One was carved in stone for the eyes of visitors and enemies. The other was buried in the ground. A machine of ceramic and calculation that kept the first city alive. We still don't know how every component functioned. Some cisterns remain unexcavated. Some pipe networks disappear into collapsed tunnels that are too unstable to explore. The complete system died with the engineers who designed it. So the next time you see a photograph of the treasury, remember, you're looking at a distraction. The real Petra is the machine beneath the tomb. And it's been lying there, silent and invisible, waiting for someone to notice. The machine is still there. We just forgot how to turn it on. Imagine a swimming pool. Blue tiles, cool water, the sound of a fountain. Now place it in the middle of the Jordanian desert, where the temperature hits 110 degrees and rain falls only 4 inches a year. This isn't a modern hotel. This was Petra, 2,000 years ago. A city of 30,000 people who didn't just survive the desert, they humiliated it. They treated water not as a scarce resource, but as a decoration. But this paradise was a trap. By turning a survival system into a status symbol, they engineered a machine so complex that it couldn't be fixed when it broke. The story of Petra isn't about a lost trade route. It's about a civilization that died of excess. They built a garden in hell, and then they forgot how to keep it alive. The Wadi Musa receives 100 millimeters of rain per year. Almost none of it falls gently. It arrives as flash floods, violent walls of water that tear through the narrow canyons, carrying tons of sediment, debris, and dissolved rock. These floods last minutes, sometimes hours. Then the sun returns, and the valley becomes a furnace. For most civilizations, flash floods are disasters. For the Nabataeans, they were harvests. They built a capture network. 210 cisterns carved directly into the sandstone hills, positioned at specific elevations to form a cascade system. When the winter storms came, water would funnel through engineered channels, filling each reservoir in sequence from highest to lowest. Total storage capacity, approximately 40 million liters. But raw floodwater is unusable. It's liquid, mud-suspended clay, organic matter, mineral salts that would poison crops and corrode pipes. The Nabataeans solved this with particle filtration basins. These weren't simple holes. They were engineered settling tanks with calculated dimensions. Water enters at high velocity, then spreads across a wide, shallow basin. Physics takes over, flow rate drops, turbulence decreases, and gravity pulls particles downward. Heavy sediment settles first, sand and gravel sink within minutes. Lighter clay particles take hours. The cleanest water, now 90% sediment-free, exits through overflow channels positioned at the basin's edge, several inches above the floor. The result, flash floods became drinking water within 24 hours. Then came the distribution network. 12 miles of terracotta piping connecting springs, cisterns, and delivery points throughout the city. The pipes weren't uniformed, they varied in diameter from 10 to 20 centimeters, depending on location and function. Narrow pipes increased flow velocity, preventing sediment accumulation. Wider pipes reduced pressure at vulnerable junctions. The gradient was everything. Too steep, and water pressure would crack the ceramic joints. Too shallow, and the system would stagnate. They maintained an average slope of 0.3 to 0.5 degrees precise. Enough that modern surveyors, measuring the ruins, still find it remarkable. This was survival engineering. Brutal pragmatism applied to a hostile environment. Every pipe served a function. Every cistern was placed with purpose. There was no waste, because waste meant death. And it worked. By the 1st century BC, Petra controlled the incense trade routes between Arabia and Gaza. They were wealthy, secure, and utterly dependent on a machine that had never failed. That's when they made the mistake. They confused reliability with invincibility. Wealth changes priorities. The Nabataeans stopped asking, "How do we survive?" and started asking, "What can we build?" The answer was the garden and pool complex. Located adjacent to the great temple in the city center, this wasn't infrastructure, it was theater. Archaeological excavations reveal a terraced garden covering approximately 3,500 square meters, featuring ornamental date palms, flowering shrubs, channeled streams, and 3 decorative pools. The largest pool measures 43 by 23 meters, with a depth of approximately 2 meters. That's 1.98 million liters of water. Not for drinking. Not for agriculture. For display. But here's what makes it engineering madness. The pools were elevated. They sat on terraces above the valley floor, requiring water to be pumped uphill against gravity. Without mechanical pumps, this meant pressure towers, elevated cisterns that used hydrostatic force to push water through sealed pipes to higher elevations. The physics are simple, but the execution is brutal. For every meter of elevation gain, you need roughly 10 meters of vertical water column to generate sufficient pressure. To supply a rooftop fountain 5 meters above street level, you need a reservoir positioned at least 50 meters higher, connected by sealed piping that can withstand the pressure without bursting. The Nabataeans built multiple pressure towers throughout the city. Stone cisterns perched on hilltops, feeding distribution networks that supplied upper-story fountains, terraced gardens, and ornamental cascades. This required constant maintenance. Ceramic joints had to be inspected, leaks sealed, pressure balance monitored. And for what? So the king could demonstrate that he had so much water, he could afford to waste it. The fountains served no practical purpose. The pools irrigated nothing edible. The gardens produced no food. They existed purely as status engineering, transforming a survival resource into a political weapon. The message was clear. We have conquered the desert so completely that we use water as decoration. But every fountain was a vulnerability. Every pool was a debt against the system's capacity. The infrastructure, built for 20,000 people surviving, was now supporting 30,000 people living in luxury. The margin for error had vanished. Maintenance crews grew larger. Specialized hydraulic engineers became essential. The knowledge required to maintain the pressure gradients, balance the flows, and prevent system failures became increasingly complex and centralized. Fewer people understood how the machine worked, and the machine had grown too large to comprehend. By the 3rd century AD, Petra's water system wasn't a network, it was an organism. Massive, intricate, and fragile. And when organisms grow too complex, they become susceptible to catastrophic failure. May 19, 363 AD, the earthquake lasted approximately 40 seconds. Magnitude 7.0, epicenter 60 kilometers northwest near the Dead Sea Rift. The rock-cut facades survived. Stone is flexible. It absorbs and dissipates seismic energy. The treasury cracked but didn't collapse. The tombs held a visible city endured. But underground, the invisible machine shattered. Terracotta pipes, rigid, brittle, held together by fitted joints, and lime mortar snapped at every junction. The pressure towers, already stressed by decades of hydrostatic force, collapsed inward. Elevated cisterns cracked, draining their contents into fractured bedrock. The settling basins filled with rubble. The ornamental pools fractured and drained into the sand. The fountains stopped first. Without pressure, the decorative jets died immediately. Then the upper terraces dried. Then the gardens wilted. Within weeks, the entire northern sector was waterless. The earthquake didn't kill Petra. It killed the machine. And without the machine, Petra couldn't exist. Here's where the tragedy becomes clear. They couldn't fix it. The system had grown too complex. Repairing a simple cistern was one thing clear: the debris, patch the cracks, refill from the next storm. But restoring pressure gradients across a multi-tiered network, rebuilding collapsed towers while maintaining water flow to 30,000 people, recalculating the hydraulic balance of a system that had taken centuries to develop, that required institutional knowledge. Engineers who understood the entire grid, administrators with the authority to coordinate repairs across the city, wealth to fund the reconstruction, and time, years of uninterrupted labor to rebuild what the earthquake had destroyed in seconds. But the earthquake had shattered more than pipes. It had broken the centralized authority that maintained the system. Trade routes shifted. Roman power was waning. The Nabataean royal administration, already weakened by generations of foreign rule, couldn't marshal the resources for reconstruction. So the machine stayed broken, and the city died slowly, deliberately, inevitably. The archaeological record shows gradual depopulation over 50 years. No mass graves, no siege layers, no fire, just absence. Families left when the fountains stopped. Merchants relocated when the trade routes dried up along with the wells. The engineers, with no system left to maintain, took their knowledge elsewhere or died without passing it on. By 500 AD, Petra was functionally abandoned. The pools had filled with sand. The gardens had returned to desert scrub. The pressure towers stood empty, monuments to a civilization that had engineered itself into extinction. Here's the irony that makes it unbearable. The Bedouin tribes survived. They lived in tents. They moved with the seasons. They relied on natural springs and carried water in skins. When the earthquake struck, their lives didn't change. They had no machine to break because they had never built one. The primitive nomads endured. The advanced city dwellers disappeared. Petra's tragedy wasn't that they lacked technology, they had too much of it. They built a system so sophisticated that only specialists could maintain it, and so complex that it couldn't survive a single point of failure. They transformed survival engineering into status engineering, and in doing so, they engineered their own obsolescence. Walk through the ruins now. The pools are dust. The fountains are silent. The pressure towers are hollow shells. But the Bedouin still live in the area, just as their ancestors did 2,000 years ago. They survived because they stayed simple. Petra died because it became too complex. The greatest engineering achievement of the ancient world wasn't brought down by barbarians or plague or famine. It was killed by excess. They built a garden in hell, and then they drowned in the machinery required to keep it alive. The swimming pool still exists, buried under sand in the northern sector. Archaeologists have excavated portions of it, the blue tiles, long gone. The ceramic piping shattered, the fountain jets collapsed. It's a monument to a simple truth. You can conquer nature, but if you humiliate it, it will wait. And when your machine breaks, nature returns to collect the debt. The Nabataeans forgot that survival is not the same as mastery. And mastery, built on complexity, is just another word for fragility. The city that drowned in complexity is still there. We just forgot that the desert always wins in the end. Look at this pipe. It's made of terracotta, fired in a kiln 2,000 years ago. It looks simple, but it is doing something that should be impossible for its time. Inside this pipe, water is moving uphill. It is maintaining a constant pressure without electric pumps, without steel valves, and without modern sensors. This is the lost technology of Petra. While Rome was building roads, the Nabataeans were mastering fluid dynamics. They weren't just carving tombs. They were building a high-pressure hydraulic grid that rivals a modern city. We think of the past as primitive, but deep in the Jordanian desert, there is evidence that they knew secrets about water and gravity that we are only just rediscovering. This is the blueprint we forgot. The Nabataeans were nomads, tent dwellers, desert traders who moved with caravans between Arabia and the Mediterranean. There is no evidence they built cities before Petra. No predecessor settlements showing gradual technological development. No archaeological record of hydraulic experimentation. And then, suddenly, around 300 BC, they carved a city into a desert canyon and built a water system that shouldn't exist. This is the anomaly. Civilizations don't leap from nomadic life to advanced hydraulic engineering without transitional phases. Yet the earliest water infrastructure at Petra already shows sophisticated understanding of principles that wouldn't be formalized in Western science for another 1,800 years. Start with the cisterns. Not the number we know, there are over 200, but the shape. Many of Petra's cisterns are bell-shaped, narrow at the top, wide in the middle, narrow at the bottom. This isn't decorative. Its functional geometry designed to exploit laminar flow dynamics. When water enters a bell-shaped chamber, it spreads horizontally across the widest section. Velocity drops dramatically. Turbulence decreases. Suspended particles, sand, silt, organic debris settle in concentric layers, heaviest particles descending to the narrow bottom. Lighter particles accumulating in graduated zones above. The cleanest water remains at the top, drawn off through elevated exit channels. This is gravity-based sedimentation optimized through chamber geometry. The same principle modern water treatment plants use, executed in carved stone 2 millennia ago. But here's what elevates it from clever to extraordinary. They understood pressure equilibrium. The pipes connecting these cisterns maintain a gradient of 0.3 to 0.5 degrees, roughly a 5-meter drop per kilometer. This number isn't arbitrary. It represents the optimal balance between 3 competing forces: gravitational flow, frictional resistance, and hydrostatic pressure. Too steep, and water velocity increases, creating turbulence that erodes pipe walls and generates pressure spikes at junctions. Too shallow, and friction dominates, causing flow stagnation and sediment accumulation. The Nabataeans found the equilibrium point, where water moves at constant velocity without accelerating or decelerating. This is the Darcy-Weisbach equation, the mathematical relationship between pipe slope, fluid velocity, and friction loss. It wasn't formalized until 1857. Yet Petra's aqueducts, built in 100 BC, operate on its principles. They also understood ceramic sintering, the process of firing clay at specific temperatures to achieve desired material properties. The pipes recovered from Petra show variable porosity. Some sections are dense, vitrified, impermeable, designed to maintain pressure in sealed conduits. Other sections are more porous, fired at lower temperatures, used in filtration contexts where microporosity allows water passage while blocking particles. They were manipulating material science at the molecular level, using nothing but kill temperature control. Where did this knowledge come from? There's no evidence of borrowing from Egypt or Mesopotamia. The techniques are distinct, unique to Petra. It's as if the Nabataeans inherited a complete technical manual from an unknown source or developed it so rapidly that the archaeological record can't capture the transition. This is the anomaly. Technology that appears fully formed, without precedent, in the hands of a people with no prior engineering tradition. The real test of any technology is scale. Can it be expanded without breaking? The Nabataeans didn't just build a survival system. They built an impossible grid. Consider the pressure towers. These are elevated cisterns positioned on hilltops, connected to lower distribution points through sealed terracotta piping. The principle is hydrostatic pressure. The weight of a water column creates force proportional to its height. For every meter of vertical elevation, water at the base experiences approximately 0.1 bars of pressure. A cistern positioned 50 meters above a fountain can generate 5 bars of pressure, enough to push water uphill through pipes, against gravity, to supply rooftop gardens and ornamental jets. But here's the engineering challenge. Ceramic pipes can't withstand unlimited pressure. Terracotta has a burst strength of approximately 10 to 15 bars before the material fractures. This means every pressure tower had to be precisely calibrated, positioned at an elevation that generated sufficient force to reach its destination, but not so high that it exceeded the pipe's structural limits. The Nabataeans built at least 40 of these systems throughout the city. Each one required site-specific calculations: elevation, differential, pipe length, friction loss, destination height. There was no margin for error. Too much pressure, and the pipes burst. Too little, and the water wouldn't reach. They were performing civil engineering calculations without calculus. They were managing pressure loads without pressure gauges. They were building a city-scale hydraulic grid using pre-industrial materials and achieving performance levels that rival modern municipal water systems. Compare this to Roman aqueducts. Rome built monumental infrastructure, the Aqua Claudia, the Ponte du Gardem, impressive in scale and durability. But Roman aqueducts were almost entirely gravity-fed open channels. Water flowed downhill from source to destination. When they needed to cross valleys, they built bridges to maintain the gradient. When they reached the city, water was distributed through open tanks and channels. The Romans rarely used pressurized pipes. When they did, they used lead, which could withstand higher pressures than ceramic, but was expensive and toxic. Their understanding of pressure dynamics was limited, their calculations rudimentary. The Nabataeans, by contrast, built a pressurized network using brittle ceramic and achieved stable, controlled distribution across a multi-tiered city. They were operating at a level of hydraulic sophistication that Roman engineers wouldn't match. And they did it earlier. The garden and pool complex represents the apex of this technical mastery. 3 ornamental pools, multiple fountains, irrigated terraces, all positioned above the valley floor, all requiring pressurized delivery. The engineering precision required to maintain stable flow across dozens of simultaneous outlets, preventing pressure drops that would kill the fountains, is staggering. Modern municipal water systems use automated sensors, pressure-regulating valves, and computer modeling to maintain distribution balance. The Nabataeans used ceramic pipes, stone cisterns, and manual valve control, likely simple plug systems that workers adjusted by hand based on observed flow rates. They were running a city's water grid with analog technology and achieving operational stability that lasted centuries. This wasn't primitive. This was sophisticated engineering, executed within material constraints that would challenge modern designers. May 19, 363 AD. The earthquake measured approximately 7.0 magnitude. 40 seconds of ground motion. The visible city survived. The invisible grid shattered. But that's not what killed the knowledge. Earthquakes destroy infrastructure. They don't erase memory. The pipes could have been rebuilt. The pressure towers could have been reconstructed. The formulas for gradient calculation, the techniques for ceramic sintering, the understanding of hydrostatic equilibrium, none of that should have been lost. Yet it was. The archaeological record shows something worse than destruction. It shows forgetting. After 400 AD, there's no evidence of hydraulic engineering at Petra. Not simplified versions. Not attempted repairs. Not even failed experiments. Just absence. The knowledge disappeared. Here's what we think happened. The system was maintained by specialized engineers. Not common laborers, but trained technicians who understood the principles underlying the infrastructure. This knowledge was likely transmitted through apprenticeship master to student, generation to generation, rather than written texts. When the earthquake destroyed the grid, it created a cascading failure in the social structure. Without water, the city depopulated. Without population, there was no demand for engineers. Without work, the masters stopped taking apprentices. The knowledge chain broke. Within 2 generations, nobody knew how the system worked. The pipes were still there. The cisterns were still carved into the hills. The pressure towers still stood. But the blueprint, the intellectual framework that explained why each component was positioned at specific elevations, why pipes were angled at precise gradients, how pressure loads were calculated, was gone. By 500 AD, people were living in Petra's ruins without understanding what they were living among. The terracotta pipes became curiosities. The bell-shaped cisterns were just old holes. The pressure towers were inexplicable structures that served no obvious purpose. The technology didn't die in an explosion. It faded through neglect, forgotten by people who had stopped asking how it worked. And we still don't fully understand it. Modern archaeologists have mapped the aqueducts, measured the gradients, analyzed the ceramic composition, but there are gaps. Some cisterns show design features we can't explain. Some pipe junctions use connection methods we haven't deciphered. Some sections of the grid seem to violate the pressure calculations we expect they shouldn't work. But clearly they did for centuries. The blueprint is incomplete. And we're trying to reverse engineer a machine built by people who understood principles we're still rediscovering. Here's the tragedy. The Nabataeans solved a problem we're facing today. They built sustainable water infrastructure in an arid environment using local materials and renewable energy gravity. They achieved what modern engineers call passive systems, infrastructure that operates without external power, maintained through simple mechanical intervention. This is exactly what we need for climate-resilient design in water-stressed regions. And the solution was sitting in the Jordanian desert for 2,000 years, slowly eroding while we forgot to look. We think of history as progressor straight line, from primitive to advanced, from ignorance to knowledge. But standing in Petra, surrounded by shattered pipes that once carried pressurized water uphill without electricity, you realize progress isn't linear. Sometimes we forget. Sometimes we lose the manual. Sometimes a civilization achieves something extraordinary and then vanishes, leaving behind artifacts we can't replicate and techniques we can't explain. The terracotta pipes are still there, buried in the sand. You can pick up the fragments, feel the texture of the ceramic, see the precision of the joints. They're physical proof that someone, somewhere, knew something we've lost. The science isn't gone, it's waiting. Encoded in the angles of aqueducts, the geometry of cisterns, the composition of pipes. We just have to remember how to read it. Petra isn't a ruin, it's a library. And we forgot the language it's written in. The blueprint is there. We just don't know how to read it anymore.